All right, here we go with section 4, which is on phase changes. And we're going to start off with the energy changes accompanying phase changes. Okay, so water left uncovered in a glass for several days is going to evaporate, just like ice is going to melt in the warm room. And these changes of states of matter are called phase changes. And we talked about these last year with the 6 different names for all of them. Okay, you've got melting and freezing, you've got vaporization and condensation, you have sublimation and deposition. So let's start off there with molecules in a solid are in fixed positions with respect to one another and are arranged to minimize the energy of the system. Okay, now what happens when you have a solid, okay, when the temperature goes up, that means that my molecules vibrate even more and gain more energy. Now that energy goes to overcoming the intermolecular forces and the molecules begin to spread out. Okay. When we look at fusion or melting, either one, same thing, 2 different names, okay, your energy needed is what we call a heat of fusion. And a lot of times you'll see that delta H with like a little FUS underneath or like a subscript. So you'll see it like this. That's how much heat it takes or energy it takes to fuse something or melt it. Okay. Now, as we're looking at the temperature of a liquid phase increasing again, the molecules of your liquid move about with, again, increasing energy. So now we're talking about going from a solid to a liquid, now a liquid to a gas. They're going to have even more energy. So we gain even more energy, we're starting into our gas phase. So now our liquid molecules, again, are gaining energy, which means that we're going to try and break the intermolecular forces between them. So as they do that, now my gas molecule concentration starts to increase because now I'm the liquid, and as they break apart or stretch, now I've got my gas. So as those gas molecules start to kind of gain in concentration, now you are exerting a pressure over the liquid. And we call this vapor pressure. Okay? Now a liquid will boil, okay, when your vapor pressure equals your atmospheric pressure. When your pressure on the inside or over top your liquid equals out the pressure around it. Okay, and again, similar to the energy of fusion, your energy needed to vaporize is called your heat of vaporization. And again, you'll sometimes see like a delta H with a VAP after to the right of it. Okay. Now we kind of compare heats of vaporization and heats of fusion. Heats of vaporization tend to be larger values than heats of fusion because the transition from a liquid to a vapor stage, the molecules must essentially sever all intermolecular attractions. Whereas in melting, many of them still kind of stay together. You're just stretching them apart. So it takes more energy to break them than it does to stretch them, which should make sense. Okay. The molecules of a solid can be transformed directly into a gaseous state, and we call that the enthalpy change required for this transition, which is called the heat of sublimation, which makes sense. You're going from a solid directly severing all intermolecular forces, and you have the heat of sublimation. Okay, if we look at some examples, okay, for heats of fusion and heats of vaporization, all right, heats of fusion of ice cools the liquid in which the ice is immersed. You'll feel cool when you step out of a swimming pool because the heat of vaporization is drawn from your body as the water evaporates from your skin. So in order to evaporate that liquid that is on your skin, it takes heat from you, which makes you feel cold. All right. You can see for all of these different molecules and different substances, we have different heats of vaporization. But notice how for all of them, the blue, or the heat of vaporization, is larger than the heat of fusion. Again, it takes more energy to separate totally and sever than it does just to stretch them apart. All right, let's look now at a heating curve, which is what you just did in the lab icy hot. Okay, a heating curve is just the graph of temperature versus heat added. And it is a graph of the phase changes that were explained above. So be careful, these are not phase diagrams, okay, which are a little bit different and show every single phase on it. These are heating curves. So let's look at an example, okay. We're going to calculate the enthalpy change of a system for each of the segments of a heating curve. Okay, we have segments A, B, C, D, and E, F, where you're heating a single phase from one temperature to another. So notice how there it says A, B, the blue, C, D, and E, F. Okay, we have one single phase that you are heating up. All right. Now, the amount of heat needed to raise the temperature of a substance is given by the product of the specific heat, mass, and temperature change. Okay, so that's going to be the whole Q equals MC delta T. So the amount of heat needed to raise the temperature is given by MC delta T. Okay, so that's where we're looking at the blue ones. So actually, I probably should do that in blue. Okay. Now, the greater the specific heat of the substance, the more heat you need to accomplish a certain temperature change. Okay? Since the specific heat of water is greater than the specific heat of ice, the slope of CD is less than AB. Notice how AB is a little more straight up and down than CD is. That is because the specific heat of water is more than the specific heat of ice. Higher C, or higher specific heat. That means that it takes more heat to go up 1 degree. So if you're going to go up 1 degree, I need to go a lot more to the right to go up my 1 degree, which makes my slope less. I need a lot less to go over in my heat. So my slope here is a lot higher. Okay, but we're talking only about the blue sections here, which are one state of matter. Now, segments B, C, and D, E are converting one phase to another at a constant temperature. So here, your temperatures are not changing on these red lines. Okay, you're changing phases. So the temperature remains constant because the added energy is used to overcome the attractive forces between molecules rather than to increase their kinetic energy. So instead of increasing a temperature, okay, we're increasing or splitting your molecules apart. Okay, so when you're changing phases on these straight lines, because your temperature is not changing, because all of that energy, instead of going into changing temperature, it's going into breaking my bonds apart. So you can use the heat of fusion for the BC line, which is delta H fusion, and you can use the delta H of vaporization to calculate the total heat change for our heating curve. Okay, and that's only going to depend on how many moles you have. So depending on how much you have, these heats of fusion and heats of vaporization are going to change. But notice how there's no temperature change, so there's no MC delta T here. It's just depending on how much of them you have. How many bonds am I trying to split apart? Because there's a set number for 1 mole. The more moles you have, the more heat it takes. All right, so let's take a look at a practice problem with trying to figure out the enthalpy change using kind of these heating curves as a guide to help you out to figure out how to figure out the enthalpy change for each one. So first off, you kind of got to divvy this up into different degrees because it says calculate the enthalpy change upon converting 1 mole of ice at negative 25 degrees Celsius to water or vapor, okay, or to water vapor or steam at 125 degrees Celsius under a constant pressure of 1 atmosphere. The specific heats of ice, water, and steam, and they list those three. They give the heat of fusion and the heat of vaporization, okay? And so we got to figure out the total enthalpy change. So if we're looking at one of these charts, okay, of the heating curves, you're going to have to figure out how much heat did you go from A to B, heat from B to C, C to D, D to E, E to F. Because we're going all the way from negative 25 to 125, all the way from one end to the other end, all through the phase changes. Well, sometimes the temperature changes, and sometimes it doesn't. Okay, so remember we're using the Q equals MC delta T for when our temperature is changing, and we're using the heats of fusion and heats of vaporization for when you're breaking the bonds or stretching the bonds apart, and that is based on how many moles you have. So let's start out here and look at the first temperature range, which is negative 25 degrees Celsius to 0 degrees Celsius, because that is the part of the chart down here on the lower left, okay, where we have just ice. So we go from 0, or negative 25 to 0. So we go from negative 25 to 0. We are changing temperature, obviously. So we're going to Q equals MC delta T to figure out our heat. Okay? Well, we've got 1 mole of ice, Okay, that means I have 18.02 grams because that's how many grams are in a mole, H2O, add it up. Okay, so I'm going to have Q equal to 18.02 grams. The C, okay, for ice is the 2.03 joules per gram Kelvin. And my temperature change is 25 degrees Celsius, run from 0 to 25. So that means what my heat here is going to be, when you multiply, 914.5 joules. So that's the first section. Okay. Now I'm going from negative 25 to 0, which is going to be ice. Now if we look back at our chart, now I have the ice-water mixture. Now that I'm at 0, it's no longer really melting, okay, where it's one state. Now it's two states. I've got ice and water, where my ice is melting and my water is kind of getting more of it. So I'm not changing temperature at 0, which means I need the heat of fusion. So that means at 0 degrees, which is 0, if you want, to 0, okay, we're melting. So that's going to be the delta H for fusion. And again, remember, that's based on how much we have. Now it tells me that that is 6, my Q, which is delta H, same thing here, is 6.01 kilojoules per mole. Well, how many moles do I have? I have 1 mole, so times 1, which is going to be 6.01 kilojoules. I'm going to keep it all in the same units. That's going to be 6,010 joules, just so that I have all the same units. I'm going to add all these Q's up. Okay, now I'm going to go, now that I've melted, okay, now I'm going to change temperature, and I'm going to go from 0 degrees to 100 degrees. Because that is a place on my chart now where I have just a liquid. So you're heating up the liquid. Okay, I don't have a vapor yet. I've got just a liquid from 0 to 100. Okay, so now I'm going to do the same thing I did before with the Q equals MC delta T. My delta T is going to be different, and my C is going to be different because I don't have ice anymore. So Q equals, still the same mass, 18.02 grams. I look there on the C, and it tells me that that is 4.18. And that is joules per gram Kelvin. And my delta T is 100 because we're from a 0 to 100. So that means then that my Q is going to be, when I multiply all that out, 7,532 joules. Okay? Now that I've got my liquid, all right, now I melted it, got the liquid, now I have to vaporize it, pull those bonds apart. So now I'm going from 100 to 100, where you're vaporizing it. So this is going to be the delta H of vaporization. And that one they tell me in the problem is 40.67 kilojoules per mole. Well, I still have 1 mole. So that's going to be the same number, 40.67 kilojoules. Well, I don't really want it in kilojoules. I'd much rather have it in joules so I can get them all together. So I'm going to have 40,670 joules. Takes a lot more energy to vaporize. Makes sense. Okay, the delta vaporization should be bigger. Now, okay, I'm vaporizing. So now we are in that we passed the straight line across for the vaporization. Now with that little end part, we're going to go from 100 to 125. Because that's where we're going to be raising the temperature. I'm going to have just water vapor. So Q equals MC delta T, 18.02 grams. The C now for vapor, okay, is 1.84 joules per gram Kelvin. And my delta T is 25 degrees Celsius. So I get my Q, and we are going to get 828.9 joules. I'm going to take all of those joule numbers that I have, and that's going to be the total enthalpy change for the entire thing. So 914.6 plus 6,010 plus 7,532 plus 40,670 plus 828.9. And we are going to get 55,955 joules, which is the same thing as 55.96 kilojoules. And that is the amount of heat it takes to change from a solid all the way up into the gas. All right, the last thing in this section is critical temperature and pressure. Okay, a gas normally liquefies at some point when pressure is applied to it. All right. You're taking the gas particles and you're scrunching them down really close together. While a cylinder with a piston attached to it contains water vapor at 100 degrees Celsius. If the pressure is increased, okay, liquid water will form and the pressure is 760 torrs. If the temperature is 110 degrees Celsius, the liquid phase doesn't form until the pressure is 1075 torrs. And then at a higher temperature, it doesn't form until 165,000 torr. And then above this temperature, no amount of pressure will cause a distinct liquid phase to form. Okay? As the pressure increases, the gas will only become steadily more compressed. At a certain temperature, no pressure will make a liquid. It's kind of like it's hard to tell between a liquid and a gas. Okay? And what happens here, we call that is a critical temperature. That is the highest temperature at which a liquid phase will form. Okay? At temperatures higher than a critical temperature, the particles have too much energy and can't liquefy. And when we look at intermolecular forces with this, okay, the greater the intermolecular forces, the greater the critical temperature. Now, if you look at then what we call critical pressure, okay, that is the pressure required to liquefy at the critical temperature. And we see here in the chart some critical temperatures and critical pressures of certain substances. Now notice how our highest one here is water for critical pressure and critical temperature, which makes sense because it has a very large intermolecular force of our hydrogen bonding. Whereas argon is a nonpolar, so it's London dispersion, so its critical pressure and critical temperature are a lot lower.